Our digital world is creating this, well, an almost unimaginable amount of information. We're talking everything from healthcare and climate science to, our own personal photos. We're saving it all. But this data explosion, it's creating a real crisis. So, what are we going to do? Well, let's dive into a revolutionary solution that's been hiding in the code of life itself.
Okay, get ready for this number, 5,000 zettabytes. That's a 5 with 24 zeros after it. It's the insane amount of data our world is projected to generate by the year 2040. And to put that into perspective, a single zettabyte is a billion terabytes. This isn't just some abstract number. This kind of exponential growth presents a massive physical storage challenge.
So it all comes down to this, right? Where are we going to store all of this stuff? I mean, our current technology, your hard drives, flash memory, even these huge data centers, they're already feeling the strain. We are, quite literally, running out of space, and the energy it takes to keep it all running is just becoming unsustainable.
So here's the game plan for this explainer. First, we're going to unpack the data storage dilemma we're all facing. Then we'll look at nature's absolutely incredible solution. We'll break down how we can translate digital files into biological molecules, weigh the promise against the practical challenges, and then finally, see how the world is actually coming together to build this new future.
All right, let's kick things off with the problem. The core issue is simple. Our ability to generate data is just completely outpacing our ability to store it affordably and sustainably for the long haul.
This quote from Dave Landsman at Western Digital, it just hits the nail on the head. Businesses, researchers, even governments are being forced to make these impossible choices about what invaluable information to keep and what to just discard. Why? Simply because they can't afford the cost, the space, and the energy to save it all. This isn't just about saving files. We're talking about potentially losing future discoveries.
And that's not even the whole story. The other part of this dilemma is that traditional storage media just isn't built to last forever. Hard drives, tapes, they have to be replaced every 3 to 7 years because they physically wear out. This constant process of copying data to new media, it's called a technology refresh, and it is expensive, it's energy intensive, and it's just not sustainable at the scale we're talking about.
Okay, so what if the perfect storage medium has been here the whole time, hiding in plain sight? What if nature had already spent billions of years perfecting a way to store just massive amounts of complex information in a tiny, stable, and super durable format? Well, it has. The solution is DNA.
When it comes to DNA, there are 3 just game-changing advantages. First, it's hyperdense. That means you can store an incredible amount of data in a tiny, tiny amount of space. Second, it's ultra-persistent. It can literally last for thousands of years. And finally, it's sustainable. It needs 0 electricity to maintain the data once it's stored. Okay, let's really wrap our heads around that density. Theoretically, a single gram of synthetic DNA, that's about the size of a teardrop, could hold 215 petabytes of data. Remember, a petabyte is 1,000 terabytes, so that 1 gram could hold the same amount of data as thousands of modern tape cartridges. The contents of an entire warehouse-sized data center could literally fit in the palm of your hand.
And then there's durability. I mean, this is just incredible. Scientists have successfully pulled out and sequenced DNA from a relative of the mammoth that was 2 million years old. Now, compare that to a hard drive that might last a decade if you're lucky. As long as you keep it safe from things like UV light and oxygen, DNA is an unbelievably stable archive.
Okay, this all sounds like science fiction, right? So how does it actually work? How do you take a digital file, like a document or a video, and turn it into a physical molecule? Let's break it down. Esther Singer from Twist Bioscience puts it really simply. At its core, any file is just a long string of zeros and ones. So the first step is to translate that binary language into the language of biology, the 4 nucleotide bases of DNA, adenine, cytosine, guanine, and thymine. A, C, G, and T. So how do you do that translation? Well, it's handled by something called a codec. Think of it like a digital Rosetta Stone. The codec is basically software that has a set of rules for converting all those zeros and ones from a computer file into a specific sequence of A's, C's, G's, and T's. It's also smart enough to build an error correction to make sure the data can be read back perfectly. So the whole process breaks down into 4 main steps. First, the codec encodes your binary data into a DNA sequence. Second, a machine actually synthesizes or writes real DNA molecules with that exact sequence.
Third, these molecules get stored, maybe in a little drop of liquid inside a tiny steel capsule. And finally, to read the data back, a DNA sequencer figures out the order of the bases, and the codec translates it right back into your original digital file.
So you might be wondering, if this is so revolutionary, why isn't it everywhere already? Well, like with any groundbreaking technology, there's a pretty big gap between the incredible promise and the, practical reality of today.
Well, the single biggest hurdle, and it's a big one, is cost. Storing 1 gigabyte of data on a hard drive costs less than 3 cents. Storing that same gigabyte in DNA, about $3,500. Yeah. Until that cost comes way, way down, DNA storage is going to be limited to really specialized long-term archival stuff.
And it's not just about the cost. There's also speed to consider. The chemical processes of writing and reading DNA, well, they're getting faster, but they're still much, much slower than just accessing a hard drive. This makes it totally unsuitable for data you need to get to quickly or often. It's really designed for write once, store forever type situations.
And hey, let's just clear up a common misconception right now, because it's a funny one. This is not some sci-fi movie where we're injecting data into living creatures. As Dave Lantzman humorously points out, the DNA molecules we use for data storage are synthetic. They're custom-built just to hold data. They have no biological function, no genes, zero risk of creating life.
So how do we bridge that gap? From this amazing but expensive tech to a real, practical solution? The answer is all about collaboration.
Esther Singer really said it best. No single company can build this entire ecosystem alone. It's going to take experts from bioscience, from chip manufacturing, data storage, software engineering, all of them working together toward one common goal.
And that is exactly what's happening with something called the DNA Storage Alliance. You've got these huge tech players like Microsoft and Google, storage giants like Western Digital, and biotech innovators like Twist Bioscience all joining forces. Their goal? To create an interoperable ecosystem so all the different technologies can work together, seamlessly.
What the Alliance is trying to do is create a common playbook, a set of standards and rules for how DNA storage should work. By defining the rules of the road, they can speed up development and make sure that new tools and innovations from all these different companies will be compatible, helping the whole ecosystem just grow faster.
When you really boil it down, DNA offers a path to a much more sustainable data future. It's a storage medium that is thousands of times more dense, more durable, and way more energy efficient than anything we've ever come up with. It truly is nature's ultimate hard drive.
So that leaves us with this one big thought. The challenges, yeah, they're significant, but the progress is real. And if we can solve for cost and speed, we might be on the verge of a world where our most precious data, our art, our science, our entire history, is preserved for millennia, written not in fleeting magnetic bits, but in the timeless language of life itself.